Part 1. General Theory. 1. Magnetism and electric current. A magnet pole attracting or repelling another magnet pole of equal strength at unit distance with unit force is called a unit magnet pole. The space surrounding a magnet pole is called a magnetic field of force or magnetic field. The magnetic field at unit distance from a unit magnet pole is called a unit magnetic field and is represented by one line of magnetic force per square centimeter. From a unit magnet pole, a total of 4 times pi lines of magnetic force issue. The total number of lines of force issuing from a magnet pole is called its magnetic flux. The magnetic flux, denoted as phi of a magnet pole of strength m, is phi equals 4 times pi times m. At a distance r from a magnet pole of strength m, and therefore of flux phi equals 4 times pi times m, the magnetic field has the intensity h equals phi divided by 4 times pi times r squared, which reduces to h equals m divided by r squared height. Since the phi lines issuing from the pole distribute over the area of a sphere of radius r, that is, the area 4 times pi times r squared. Note: unit force is defined as the force that, at a distance of 1 centimeter, gives a mass of 1 gram and acceleration of 1 centimeter per second squared. A magnetic field of intensity H exerts upon a magnet pole of strength m a force equal to m times H. Thus, 2 magnet poles of strengths m1 and m2 at a distance r exert upon each other the force m1 times m2 divided by r squared. Electric currents also produce magnetic fields. That is, the space surrounding a conductor carrying an electric current forms a magnetic field, which appears, disappears, and varies with the current producing it. This magnetic field is an essential part of the phenomenon called an electric current. Thus, an electric current represents a magnetomotive force abbreviated as mmF. The magnetic field of a straight conductor consists of lines of magnetic force surrounding the conductor in concentric circles. The intensity of this magnetic field is proportional to the current strength and inversely proportional to the distance from the conductor. Unit current is defined as the current which, in a straight conductor, produces unit field intensity at unit distance from the conductor. That is, it creates 1 line per square centimeter in the magnetic circuit of a length of 2 pi centimeters surrounding the conductor as a concentric circle. Alternatively, it produces twice this field intensity at unit distance from a closed current loop, which consists of the conductor and its return conductor. 1/10 of unit current is the practical unit called 1 ampere. 1 ampere turn produces at unit distance from the conductor the field intensity 0.2. At a distance r, the field intensity is 0.2 divided by r. For f ampere turns, the field intensities are h equals 0.2 times f and h equals 0.2 times f divided by r. Here, f, which is the product of amperes and turns, is called magnetomotive force. The magnetomotive force per unit length of the magnetic circuit, or the ratio. Magnetomotive force divided by the length of the magnetic circuit is called the magnetizing force. Thus, at unit distance from the conductor of a loop with f ampere turns magnetomotive force, the magnetizing force is F equals F divided by 2 times pi. At a distance r, the magnetizing force is F equals F divided by 2 times pi times r. Since the field intensity at distance r is h equals 0.2 times f divided by r, we have h equals 0.4 times pi times f, which equals approximately 1.257 times f. If a conductor is coiled in a spiral of L centimeters length and n turns, the number of turns per centimeter length of the spiral is N equals N divided by L. If I is the current in amperes passing through the conductor, the magnetomotive force of the spiral is large F equals N times I. The magnetizing force in the middle of the spiral, neglecting the reaction of the ends, is large F equals N times I, which equals N divided by L times I. Field intensity in the middle of the spiral or solenoid is H equals 0.4 times pi times F, which equals 0.4 times pi times N times I. That is, 1 ampere turn per centimeter length of the magnetic circuit produces 0.4 times pi, which equals approximately 1.257 lines of magnetic force per square centimeter. 10 amperes, or unit current, per centimeter length of the magnetic circuit produces 4 times pi lines of magnetic force per square centimeter. That is, unit current is the current which, when acting upon a magnetic circuit in air of unit length, or 1 centimeter, produces the same number of lines of magnetic force per square centimeter, 4 times pi, as issue altogether from a unit magnet pole. Magnetomotive force, denoted as large F, applies to the total magnetic circuit or part of the magnetic circuit. It is measured in ampere turns. Magnetizing force, denoted as small f, is the magnetomotive force per unit length of the magnetic circuit. It is measured in ampere turns per centimeter. Field intensity, denoted as H, is the number of lines of force per square centimeter. If L represents the length of the magnetic circuit or part of the magnetic circuit, large F equals L times small f, and rearranging, small f equals large F divided by L. From this follows that H equals 0.4 times pi times small f, which equals approximately 1.257 times small f. Transposing, the magnetizing force is small f equals H divided by 0.4 times pi, which equals approximately 0.796 times H. The preceding applies only to magnetic fields in air or other non-magnetic materials. If the medium in which the magnetic field is established is a magnetic material, the number of lines of force per square centimeter is different and usually many times greater. In diamagnetic materials, it is slightly less. The ratio of the number of lines of force in a medium to the number of lines of force that the same magnetizing force would produce in air, or rather in a vacuum, is called the permeability or magnetic conductivity, denoted as μ of the medium. The number of lines of force per square centimeter in a magnetic medium is called the magnetic induction, denoted as B. The number of lines of force produced by the same magnetizing force in air is called the field intensity, denoted as H. In air, magnetic induction B and field intensity H are equal. As a rule, the magnetizing force in a magnetic circuit is changed by the introduction of a magnetic material due to the change in the distribution of the magnetic flux. The permeability of air equals 1 and is constant. The permeability of iron and other magnetic materials varies with the magnetizing force, ranging from slightly above 1 to about 4,000 in soft iron. The magnetizing force, denoted as small f in a medium of permeability μ, produces the field intensity H equals 0.4 times pi times f, and the magnetic induction B equals 0.4 times pi times μ times f. Examples: 1. To hold a horizontal bar magnet of 12 centimeters length, pivoted at its center, in a position at right angles to the magnetic meridian, a pull of 2 grams at a radius of 4 centimeters is required. What is the intensity of the poles of the magnet and the number of lines of magnetic force issuing from each pole, given? The horizontal intensity of the terrestrial magnetic field H equals 0.2, and the acceleration of gravity equals 980. Assume the distance of the poles of the bar magnet is 5/6 of its length. Let m equal the intensity of the magnet pole, and r equals 5, the effective radius on which the terrestrial magnetism acts. Thus, the torque exerted by the terrestrial magnetism is 2 times m times h times r equals 2 times m. The 2 grams of weight correspond to a force of 2 times 980, which equals 1,960 units of force. At a radius of 4 centimeters, the torque is 4 times 1,960, which equals 7,840. Hence, 2 times m equals 7,840 and m equals 3,920. The strength of each magnet pole is 3,920. The magnetic flux phi is phi equals 4 times pi times m, which equals approximately 49,000. Thus, the number of lines of force issuing from each pole is approximately 49,000. 2. A conductor carrying 100 amperes runs in the direction of the magnetic meridian. What position will a compass needle assume when held vertically below the conductor at a distance of 50 centimeters, given the intensity of the terrestrial magnetic field is 0.2? The intensity of the magnetic field due to 100 amperes at 50 centimeters from the conductor is H equals 0.2 times I divided by R, which equals 0.2 times 100 divided by 50, or 0.4. The direction of this field is at right angles to the conductor, which is at right angles to the terrestrial magnetic field. If phi equals the angle between the compass needle and the north pole of the magnetic meridian, L equals the length of the needle, and M equals the intensity of its magnet pole, the torque of the terrestrial magnetism is H times M times L times sine of phi, which equals 0.2 times M times L times sine of phi. The torque due to the current is 0.2 times I times M times L times cosine of phi divided by R, which simplifies to 0.4 times M times L times cosine of phi. In equilibrium, these torques are equal. 0.2 times M times L times sine of phi equals 0.4 times M times L times cosine of phi. Dividing through by M times L, this simplifies to tangent of phi equals 2 and phi equals 63.4 degrees. 3. What is the total magnetic flux per L equals 1,000 meters length passing between the conductors of a long-distance transmission line carrying I amperes of current if D equals 0.82 centimeters, is the diameter of the conductors, number 0B and SG, and D equals 45 centimeters is their distance from each other? At a distance x from the center of one of the conductors, the length of the magnetic circuit surrounding this conductor is 2 times pi times x. The magnetomotive force in ampere turns is I, and the magnetizing force is F equals I divided by 2 times pi times x. The field intensity is H equals 0.4 times pi times F, which equals 0.2 times I divided by x. The flux in the zone between x and x plus dx is d phi equals 0.2 times I times L times dx divided by x. The total flux from the surface of the conductor to the next conductor is phi equals the integral from d divided by 2 to d of 0.2 times I times L times dx divided by x. This simplifies to phi equals 0.2 times I times L times the natural logarithm of 2 times d divided by d. The same flux is produced by the return conductor in the same direction. Thus, the total flux passing between the transmission wires is 2 times phi equals 0.4 times I times L times the natural logarithm of 2 times d divided by d. For 1,000 meters, which is equal to 10 to the 5th power centimeters in length, 2 times phi equals 0.4 times 10 to the 5th power times I times the natural logarithm of 2 times d divided by d. Substituting the value of the natural logarithm, approximately 4.7. 2 times phi equals 0.4 times 10 to the 5th power times 4.7 times I, which equals 188 times 10 to the 6th power times I. This is equal to 0.188 times I megalines, or millions of lines per 1,000 meters, of which 0.094 times I megalines surround each of the two conductors. 2. Magnetism and EMF. In an electric conductor moving relatively to a magnetic field, an electromotive force, or EMF, is induced proportional to the rate at which the conductor cuts the lines of magnetic force. Unit EMF is defined as the electromotive force induced in a conductor cutting one line of magnetic force per second. 10 to the 8th power times unit EMF is the practical unit, called the volt. Coiling the conductor n times increases the EMF by a factor of n, as each line of magnetic force is cut n times. In a closed electric circuit, the EMF produces an electric current. The ratio of EMF to the electric current produced is called the resistance of the electric circuit. Unit resistance is defined as the resistance of a circuit in which unit EMF produces unit current. 10 to the 9th power times unit resistance is the practical unit, called the ohm. The ohm is the resistance of a circuit in which 1 volt produces 1 ampere. The resistance per unit length and unit cross-sectional area of a conductor is called its resistivity, denoted as ρ. The resistivity ρ is a material constant that varies with temperature. The resistance R of a conductor with length L, cross-sectional area S, and resistivity ρ is R equals L times ρ divided by S. If the current in an electric circuit changes, starts, or stops, the corresponding change in the magnetic field of the current induces an electromotive force in the conductor carrying the current. This is called the EMF of self-induction. If the EMF in an electric circuit moving relatively to a magnetic field produces a current in the circuit, the magnetic field produced by this current is called its magnetic reaction. The fundamental law of self-induction and magnetic reaction states that these effects occur in a direction that opposes their cause. This is known as Lentz's law. Thus, the EMF of self-induction is in the opposite direction during a rise in current, and in the same direction as the EMF, producing the current during a decrease in current. The magnetic reaction of the current induced in a circuit moving out of a magnetic field is in the same direction. In a circuit moving into a magnetic field, it is in the opposite direction to the magnetic field. Essentially, this law is a conclusion derived from the law of conservation of energy. One, an electromagnet is placed so that one pole surrounds the other pole cylindrically, as shown in Figure 3. A copper cylinder revolves between these poles at 3,000 revolutions per minute. What is the EMF induced between the ends of this cylinder if the magnetic flux of the electromagnet is phi equals 25 megalines? During each revolution, the copper cylinder cuts 25 megalines. At 50 revolutions per second, the cylinder cuts 50 times 25, which equals 1,250 megalines per second. Thus, the induced EMF is E equals 1,250 volts.